losing my voice a little bit, so hope you'll bear with me. This is a paper with Federico and Fedor, and this is right now the first time we've ever been in a room together, despite collaborating for like 4 years. This is a COVID collaboration. So the paper is about two-sided matching markets without money, and we've already been talking about stability. Stability has kind of come to be one of the key design objectives in these markets. But stability is a kind of combinatorial condition. And it's not so clear how to compare it to other types of objectives that we sort of have our planners optimize, things like fairness and welfare and these sorts of things. And so what we're going to do is we're going to think about how stability compares to other notions with a particular class of preferences. And these preferences are those we call aligned. So typically in two-sided matching, there's two sides. They have preferences over each other, ordinal preferences, but completely independent. What we're going to focus on are preferences which are aligned, where there's a utility function which just tells you the value to both participants of every match. And so that puts some correlation structure on the preferences across the two sides. And so, we've been talking about deferred acceptance, but with aligned preferences, the stable matching is even easier to find than deferred acceptance. So here's a simple example with 3 agents on either side, and I've written all their utilities in this array. And stability as an objective, you could see that well, look at x1, y3. They better be matched together, right? Because they generate a utility 8 from being matched together. And so if you don't match them together, they're going to be getting something lower than that, and they're going to want to leave their partners and match together. So x1, y3 better be matched together. And then that just leaves the remaining pool of agents where you repeat this process. So then x3, y2 need to be matched together, and that just leaves x2, y1. Okay, so the stable matching is, at least in this finite case, fairly simple to describe. But there's other objectives one might be interested in optimizing. For example, you might want to maximize utilitarian welfare. That is, find the maximum weight matching with these weights. You might also care about maximizing the minimum match value, like a kind of a Rawlsian fairness notion. And in this example, both, I don't know if you can see, but both of these matchings are both utilitarian welfare and fairness are optimized along the matching along the diagonal, where x1 was matched with y1 and so on. And so this paper is our attempt to discuss the relation between these matchings in a general model, which is capable of dealing with both finite and infinite markets. Okay, so let me just tell you, we're focusing on aligned preferences. We think that they've been studied a little bit, but we think not enough. So let me just give you a quick motivation for sources of aligned preferences. So in Becker's classic marriage model, which is a kind of a Shapley-Shubeck reinterpretation, you've got a marriage market, and every couple has a surplus they generate, and they're thinking about matching, but they're allowed to split up this surplus any way they want. And so what I get to do is I get to try and encourage a really great partner to match with me by promising to do the dishes forever. All of that has happened, all of that negotiation happens at the time of the match, and it's committed to. You might imagine that it's hard to commit to do the dishes forever. And so if instead what you do is you have the surplus, but then once you're matched, you split it using something like Nash bargaining, then you'll get aligned preferences. Another example is ride-sharing platforms, where people need to be matched with drivers. And there, what seems to us a reasonable approximation is just preferences are just, I want to be matched with somebody closer to me, less of a weight. So the negative of the distance might be a pretty good approximation for preferences. School choice is one of the most important applications of stable matching. And at first, it doesn't feel like a setting with aligned preferences at all. And indeed, it may not be, but we think that you can capture a lot of what's important in preferences with aligned preferences. So let me just kind of try and make that case. So it's kind of well documented that students prefer, also not surprising at all, students prefer schools that are close to them. Schools also generally prioritize students who are close to them. That's like one of the most important first order things. That's just like the ride sharing preferences. But you might think like, okay, students also care about school quality. I can represent all of that with a match value that's something like a function of the match from student I being matched with school S. The utility from that is maybe some function of the quality minus the distance. And notice here that like, this is supposed to be the utility from both sides matching, but it has the school quality in it, which the school presumably doesn't care about. But if you think about the school S comparing two students, then that cancels out of both sides. So this represents the ordinal preferences. You can do more to plug in more kind of features of preferences, and we think you can get a kind of reasonable approximation for what preferences should look like, even with just aligned preferences. Okay, so let me start getting to some results. I'll start by talking about matching on the line, where we have the most concrete results and pretty pictures. So matching on the line, agents are described by their types, which is just a number. Every agent has a type, which is a number. It's two populations, it's two-sided matching, it better be two populations. Two distributions over these types. And we'll assume distance predicts preferences. So my utility for matching X to Y is just the negative of the distance on the line. What's a matching? Well, a matching is a distribution on the product X cross Y with the appropriate mergings. And let me denote by this the set of all matches. So just a quick example to show the kind of pictures we're going to be using. So imagine mu is uniform on -1, 0, and nu is uniform on 0, 1. What I'm going to do sometimes is like draw pictures and flip one of the distributions over the axis. So I can plot two distributions at the same time without them interfering with each other. So we have two distributions here. There's many possible matchings. The assortative matching, where every X type is matched with somebody a unit to the right away. The anti-assortative matching, where they're sort of flipped across reflected across the 0. You could match them completely at random, these sorts of things. Now, matching is stable if for any two matched pairs in the support of a matching, the utility from a mismatched couple, so X from one couple and Y prime from another, is less than the max of the utility from the two pairs. And this is really intuitive. At least one member in the mismatched pair should prefer their current partner. And so that this mismatched pair is not blocking. So you might have already intuited that in this simple example, the anti-assortative matching is stable, kind of thinking about this greedy algorithm. People who are close to each other should be matched first, and so forth. And that's the unique stable matching. Now, what I want you to notice here is that I've drawn the matching using these half circles to show who's matched with whom. And in the stable matching, these half circles never cross. Okay, that's a general condition that's going to be true of stable matchings. So to kind of formalize that, let me describe what I mean. So for an interval with endpoints Z1 and Z2, let me denote the circle in R2 by O Z1, Z2. And the matching satisfies no crossing if for any two couples in the support of the matching, these circles don't cross. A very useful but simple lemma is that any stable matching satisfies no crossing. I'm going to, in the interest of time, skip even this proof. But it's very simple. You know, given 10 minutes, you could all do it. What's really nice is that despite this is a very simple observation, in the literature on optimal transport, the set of matchings which satisfy no crossing has been described and studied for some time. So in particular, if mu and nu admit densities F and G, then I can describe what the no crossing matchings have to look like. In particular, every no crossing matching is a convex combination of two deterministic matchings. First, you match as many X and Y that are on top of each other as possible. You get rid of all of the ideal partners, if you can. And that gets rid of all of the common mass. And then you have two disjoint populations of the remaining agents. And it turns out that the set of matchings which satisfy no crossing of these residual populations form a finite number of parametric families. And so despite the fact that what we have are these infinite dimensional, distributions, this turns the finding a stable matching into a parametric. Let me kind of show you that with a simple example. So here's an example. Again, there's two populations, one's shown above the line, one below, and the density is twice. From the interval 0, 1, the density is twice that, from -2 to -1. So I want to show you what the no crossing matchings look like here. It turns out they're indexed by a single parameter. And that parameter is the fraction of people from the leftmost interval that are matched with people from the rightmost interval. That parameter turns out to describe all of the no crossing matchings. So here I've set this parameter equal to 4/7. You could set it equal to 1, you could set it equal to 0. But varying between those, you hit all of the possible matchings which satisfy no crossing. And it turns out that in this case, so now I only have to look at a one parametric family of matchings, for this example at least. And in this case, the stable matching has this parameter set to 4/7. So no crossing is great. It leads us to only think about this parametric family of matchings. Tells us something about the structure of the set of matchings. The bad news is that the parametric family, though it's finite, it can blow up with the number of times that this residual population changes sign, like the number of intervals. The good news is that we can exploit other properties of stable matching to speed this algorithm up of just searching through the set of no crossing matchings. And we can find an algorithm that runs in m² operations where m is the number of intervals for piecewise constant densities. And this shows you that a stable matching exists and it's unique. Okay, so let me move now to general markets. Before I do that, and the point is to connect it with optimal transport. So let me tell you about optimal transport for those of you who don't know or need a refresher. So you can see, you'll see immediately this problem is like sort of similar. In optimal transport, you have two distributions over two measurable spaces. And you have a payoff function, which tells you the payoff from matching any x to any y. And the goal is to find a matching which maximizes the sum of payoffs. Now, this is not how it's usually formulated. It's usually formulated as a cost minimization problem, where P is a cost of sending a unit from X to Y. And the typical interpretation is that these are like spatial distributions of supply and demand. Like a bunch of bakeries and a bunch of cafes, and you need to send the bread. And you want to do that in a way that minimizes the transportation cost. So for our general markets, we can think of, we can accommodate really general spaces, but maybe don't worry about that too much. There's, but the general setting, we just have two general sides, a utility function, which I'm going to assume for now is continuous, and two distributions. Let me tell you about some criteria that the planner might want to maximize. And I'm going to give approximate versions because it'll be useful for the result. So let me define approximate stability. A matching is epsilon stable if this is exactly the same definition as before, but now I've put an epsilon to the right. So I've relaxed the inequality by epsilon. And so a matching is epsilon stable if there might be blocking pairs, but at least one member of the blocking pair should be getting no more than epsilon improvement. Let me define a notion of egalitarianism. So for a matching pi, define this U min of pi to be the minimum match value across the matching. So the minimum utility from any matched pair. And let U star min be the maximum that you can make this value. So it's what you would get for the worse off agents if your whole goal was to maximize their welfare. A matching pi is epsilon egalitarian if there's a subset of size at least 1 minus epsilon, where everybody's getting at least that egalitarian lower bound relaxed by epsilon. Okay, so almost everybody is getting the egalitarian bound. It relaxed slightly. Okay, so I've given you a notion of stability, approximate stability, approximate egalitarianism. Utilitarian welfare is very straightforward. You just sum up the utilities. And let me let W star be optimal welfare. It's immediate that welfare maximization is an optimal transport problem, right? This is the payoff is the utility from the match. It turns out that you can describe these other objectives as transformations of, as optimizing a payoff, which is a transformation of this utility. So let me show you what the transformation is. And this, I'll give you a family of transformations that just depend on a single. So we have the utility function U of xy. Let me define a payoff function, P alpha xy, which is just going to be a transformation of that utility. And all it is it's e to the alpha u minus 1 over alpha. Why this choice? This choice is not special. You could do lots of things. But the nice thing about this family is that as alpha gets large, this is convex. As alpha, if alpha is negative, it's concave, increasingly concave as you make it more negative. And when alpha approaches 0, this approach is just so here's the main theorem. So let pi be a solution to the optimal transport problem with payoff P alpha. If alpha is positive, then this optimal solution is epsilon stable, where epsilon is log 2 over alpha. If alpha is negative, then pi is epsilon egalitarian, where epsilon equals the max of 1 and log alpha over alpha. Okay, so let me interpret this a little bit. So this theorem tells you the existence of stable matchings and egalitarian matchings by just taking a weak limit. You have all these solutions for different alpha, take alpha large, alpha small, and you'll get solutions by taking limits of those solutions. You'll get stable matchings and egalitarian matchings by taking limits. Changing alpha, we can interpolate between these three objectives. So on one extreme, you have like fairness, a kind of Rawlsian type fairness. On the other end, you have stability. In the middle, you have welfare maximization. And so this kind of points out that fairness and stability are on opposite sides of the spectrum. So I kind of told you in the beginning that the point was to put stability in like terms with other notions. And by doing that, we see that stability corresponds to a sort of a weird objective, right? So we're very used to doing a social planner thinking about a social planner who sums up utilities but puts a concave function around it. This is like an inequality averse plan. This is the opposite. It's a planner, a stable matching corresponds to a planner who just really cares about high utilities and doesn't care about low utilities. And so in analogy with like a risk-loving decision maker, a stable matching sort of corresponds to an inequality-loving designer. 2 minutes? Okay, good, I'm just about done. These results extend to k-sided markets, where you see a 2, replace it with a k, essentially. So stability and fairness are on opposite sides of the spectrum. Stability can lead to welfare losses, as we've already seen. How bad can these be? So let me assume that the utility function is positive, and that pi is a stable matching. Then pi guarantees at least half of the optimal welfare, and pi is half egalitarian. So despite the fact that they're on sort of opposite extremes, we can bound how bad it can be. And again, 2 is the number of the sums. So let me, there's some literature on aligned preferences. Let me skip that in the interest of time and just conclude. So aligned preferences emerge when there's a common match quality. There's transfers, but no commitment power. We think aligned preferences, though they sort of are kind of simple, in fact, encode a lot of what's going on in practical matching markets. We've given a connection between matching and the transportation problem and a parametric family that interpolates between objectives, and kind of bounded how bad the stable matches can be in terms of these other objectives. Okay, thank you.